Welcome back and welcome to the end. Everybody ready for this punchline? So I don't know if this is the best punchline. Obviously, we're in the middle of a big story. So the inference is this big story. All kinds of things you can do with inference. You can do testing, you can do estimation. And I'd like the story mostly to be about estimation, although we're kind of finishing up on testing. So there's some good news and there's some bad news. So we're going to go over both of them. I don't expect you to understand all these details because you haven't had enough time practicing these problems. And I think that there's a lot to be said for just going through the minutiae and the details. So I just want you to focus on the big picture here. I'm not going to test you on testing on the final. I might have you compute a likelihood ratio or something like that, but all the nuance and comparison of different testing ideas, I'm not going to go through that. Maybe I'll have you do a one-sided test because there's no controversy there, or simple versus simple and the Neyman Pearson thing, but I'm not going to have you do what I've done in the past. If any of you have seen my old QEs or final exams, sometimes I ask a lot about the sharp test and I ask you to untangle the differences between the different paradigms because there's stark contrast to the different ways that we approach this sharp test problem. Again, for the sharp test, the question itself is weird. So, and I think that's where the debate is really stemming from. We might not be asking the right question. I'll allude to that by the end today, and that's where the controversy is. So maybe a little bit of one-sided stuff, some likelihood ratio, but we will not touch the sharp test for testing in this class. So just keep that in mind. My video cut out last time. It ran out of memory card, so the last 20 minutes were cut out. So I just wanted to put some of this stuff back on the board. Just a couple notes, review session tomorrow, 6 p.m. We'll do yes, no, maybes. And we'll do them just like we've done before. You ask me the right questions, I'll answer truthfully and try to set you up and prepare you for the exam. That's on Friday, 10:05 a.m. in this room. You get 2 hours for this one. All your materials, the last homework assignment, midterm 2 review, bless you, and maybe some extra credit if you do that MCMC. I'll give you 15% for the 3 different versions there. I can answer questions about that. Hopefully you've already started. If you've done the first 2, the other one's not too hard. Okay. From last time, we said a few things about p-values. They're cumulative probabilities. So the probability of your data and more extreme data given the null hypothesis. So you form the null distribution and you integrate over it. So in different regions, so you check tail probabilities. So the same stuff we taught you in Stat 101. So the idea is you use some test stat, you form the null hypothesis. If we were looking at an example like this, xi's are coming from a normal with mean theta, variance sigma squared. We'd like maybe sigma squared be known. You would have n observations from this. X bar is the sufficient statistic. We'd probably use that for testing if we wanted to reduce some of the algebra or computational overhead. If we were actually doing this on a computer. The test stat we would pick that we do all our inference on is the one that falls out of the Neyman Pearson lemma, so the likelihood ratio. So that would be the uniformly most powerful one. All p-values are going to be uniformly distributed under the null, and the only difference between all the different tests are their power, what happens in the alternative space. So under the null hypothesis, p-values are uniformly distributed, and here's a proof of that. So this is just the probability, so this is some probability statement. So that F is the probability under the truth. So that's how the data is actually generated, the truth being truth theta in this example. So the null distribution is shifted over to where theta naught is. So if I were testing something like this, H naught theta is less than or equal to theta naught, or theta is equal to theta naught or something like that, I would test it theta naught. So I condition on that most powerful point. So that's what this represents right here. This null distribution, I can invert it because it's a cumulative function. So it's monotone. And this is what we get. This F is pertaining to the distribution of the data, the true distribution, so this is conditioned under the truth. So if the truth is the null hypothesis, these two F's are the same, and they cancel each other out. We get back alpha. So the probability of something being less than alpha is always alpha. That's a uniform distribution. And so, again, that's not the important part. Probably the important part is what happens in the alternative space. So the power of everything. Because getting this property is pretty easy. So I could just draw from a uniform distribution, see if I got alpha, tell you to take your hypothesis in your data and put it somewhere. I don't need to look at it. But my power in that sort of analysis would be horrendous. It would be the complement of the type 1 error. So the worst thing you could probably do. Nathan and Pearson give us some good properties, especially on which test stat you should use. And I think Bayesians should follow that as well. So use the right test stat. We know what test stat it's going to be. It's going to have to do with the sufficient statistic for that parameter. And so the factorization theorem tells us about that kind of stuff. So Bayesians will be using the same test stat because they're going to be using likelihood functions. And they're always conditioned on the sufficient statistic. That's just automatic. You're conditioning on everything. You're conditioning on ancillary statistics. You're conditioning on the whole space. That's pretty cool. So Nathan Pearsonians maybe do something with p-values. I think what Nathan and Pearson were trying to do is try to explain to Fisher something that might be useful to him to understand this property, but Fisher didn't really like that too much. And the big controversy for Nathan and Pearson is Fisher wanted to use the p-value as a continuous measure. And Nathan and Pearson said it's not always a measure of the hypothesis. So it can be, but if you're thresholding the p-value, what you might be doing is calibrating error rates. And I think that's what they said. The crux of it is you have to pre-specify alpha. And if you start budging around alpha and playing mental games with yourself, you're contaminating your error rates. So if you hear people say things like, well, if I would have picked like my p-value is let's say 0.09 or something like that, and you say, well, if I would have picked an alpha level of 0.1, then my error rate is 0.1. That's a big speculative. You should have come up with the alpha level beforehand and seen that P dumped it. So that's the rub, and Fisher didn't like that because he said scientists aren't going to do that. Now, if you're doing process control, quality control, you work in industry where you get to see things over and over again, you might do that. I think one of the useful places for all of this p-value stuff in Nathan Pearson and calibrated error rates might be stemming from some of the examples in the book. If you pick a distance from the null you want to be, and you want to calibrate that type 2 error rate, you can get the sample size that you need for the type 2 error rate to be reduced to some level. Where the alpha level is going to be something that you pick in advance. And so you need to pick whatever that threshold is based off of the type 1 error rate you want to make. So you can look at those two things and try to come up with a balancing act, but that means you go out and you collect that much data, based off of whatever your pre-specified n is. So in experimental design, where we're doing real upfront experiments, we design the experiment, we go out and collect the data for a particular reason. I think it's useful, and that's what statisticians used to do. So the whole ag universe, that's how experiments were carried out. So I think there's some value there. In the big observational universe where we're just grabbing data and we can have as much as we want, I don't think that's a useful paradigm, and that's where some of the controversy comes in. Is how do I stop? Why did I pick the amount of data that I did? And if you're not thinking about that and you're not calibrating how far you need to be from the null before you reject it, I think it's all pointless. So what people are doing. And then they're surprised that reproducibility rates are in the toilet. Bayesians do things a little bit different. They're always after this, the probability of the null hypothesis given the data. So a Bayesian is always going to take the thing that they don't know and put a probability measure on it. And they're going to condition on the data. So that's the commonality between all different types of Bayesians. I haven't told you about all the subclasses of Bayesians. So you'll even hear arguments there, and it's always about how you pick the prior and why. And I think that there's enough controversy we could probably load a whole class just on that alone, but I would rather show you things where people are, at least agreeing and not totally well on the parts where everybody just has these nuanced academic disagreements. I think a lot of them can be patched up. The agreements are always about which factors you use and why. But a Bayesian's gonna get this posterior probability maybe through the Bayes factor. There's other ways to do it. You could just integrate over the null range on the posterior distribution. So this could be something like this. Integral pi theta, given our data, theta in the null space, d theta. You could also compute this way. So there's all of these things you need to realize are the same, although it's not obvious at first glance. All of this stuff is the same. It's algebra that you need to work through. This is just Bayes' theorem. Here's how you might get this. The Bayes factor relates to this. So I could rewrite that just by conceptualizing this likelihood function as f of the data given theta. They're exactly the same functions, just the conceptualization is a little bit different. But mathematically, the expression is the same. Obviously, I'm going to move theta, so I might want to call it a likelihood. To describe that's what I'm doing with it. What is the mathematical expression? It's the joint distribution of the data given theta. So that's the algebra on the board. So if I didn't tell you what the expression was or what I was going to do with it, I just wrote it on the chalkboard, you wouldn't be able to distinguish it's a likelihood or a sampling function until I told you which argument I was going to move over. So this is just the marginal distribution of the data conditioned on the null hypothesis divided by the marginal distribution of the data given H1. So that's what you would work out right there. And so from this expression right here, you can kind of see that this is one part of this right here. So we'll introduce some new notation. I might put weights on the hypotheses. So these are just probability weights, the way I've written it. The hypotheses are discrete, so those are just mass functions. And how I want to weight those different things. Keep in mind, there's a continuous part to the prior and how I smear mass across the hypotheses. And that does make a big difference. So if you want to just work out the algebra and take this formula, maybe plug that in for the Bayes factor and rearrange everything, you'll get this. So they're the same. And at least maybe you can believe it just by eyeballing it. Dylan, don't work out all the algebra right now. That's not the important part. You can do that right afterwards. But I get it. Sometimes you like to practice your algebraic skills. So it's not too hard to work through. So Bayesian always does this. Although sometimes when they do things like this, it doesn't look exactly the same. But if you worked all this out, it would be the same. It'd be identical. Let me give you some good news. We said this last time. I think it got cut out of the video. So for this test, H naught, theta is less than theta naught. So I'm still kind of thinking about this example. Just for context, if I were doing the one-sided test, and in your Stat 101 class, they might do this to try to not confuse you. And you get what they're doing now. They're taking that point on the boundary of the space that is the point you would want to test at, because it gives you all the information. So why would I budge myself from the boundary when I kind of want to look over the cliff and see what's going on the other side? So I like to write it like that. For this right here, if the Bayesian, take this, if the Bayesian uses pi naught is equal to 1 minus pi naught. So they balance those prior weights. So this is just the probability of the null hypothesis. This is the probability of the alternative hypothesis. That's obviously got to be 1/2 because they're positive, they're probabilities. So if we pick this to be maybe the objective prior and balance out our weights that we put on the hypotheses, which I think makes sense if you didn't know anything. So there probably are cases where you know things. It's like you have this imbalance between the two sets, and maybe you know that up front. So maybe spams, no spams, or something like that. So when I first got to the university, maybe I got a lot of just normal emails from people, but once my email got around after a couple of years, I'm inundated. So I'm just flooded with spams. So I might change those probabilities. So if you're changing those weights in dealing with different imbalances in samples, and you're using software packages to do this for classification algorithms, I can almost assure you this is what they're doing, is playing around with this in a Bayesian sense. So, and I'm going to say this, pi h naught theta and pi h1 theta are both proportional to the same constant. So flat prior on both. Now I did say something about using a flat prior here. Don't do it unless you know what's going on. In this case, it's okay, because the parameter means the same thing on both sides of the space, and there's this balancing act between doing this. If you use the exact same improper prior with the same constant, usually I pick that name to be, that constant to be 1. What you would get is the p-value is equal to the posterior probability interval. And I would say these are pretty reasonable priors considering the hypothesis that we're testing. If you want to think about this a little bit differently and you're uncomfortable calling this a distribution, because it's not. It's this thing that integrates off to infinity. You could consider this maybe the conjugate prior, the normal prior on theta, where the variance is super large, and then take whatever that super large number is and power it up to that super large number, and do it again, and do it again, and do it again, and do it again. Still proper prior. It will converge to this result. So if you're not comfortable using limits on priors before you do the analysis, you can take that limit afterwards and you'll get this result. So they converge into each other. So there's an agreement between the Bayesian and the non-Bayesian. The Bayesian thinks of this as their belief that this is actually true. So it's a probability statement about it, where the p-value is still just playing around with error rates. So they're still calibrating error rates. So the conceptualization is different, but you get two different properties that have the exact same answer. So I kind of like that. I would say there's no disagreement. There's a unification. For this hypothesis, the simple versus simple, theta is equal to theta naught. Theta is equal to theta 1, so just 2 points. As long as we've got pi naught is equal to 1/2, so 1 minus pi naught is also 1/2. So we balance this. If I just had 2 points in the space, and I was trying to be objective and not put weight on one, I didn't know anything extra, this seems like a reasonable thing to do, and it's almost hard to justify anything other than this. So I'd have to have really good reasons for doing that. I have seen people play around with this a little bit, where they'll do the game a little bit differently and try to figure out human behavior and say, let's figure out how biased you are. So if you don't believe this, what is your prior? Because the data is telling you something else. And some people will do that. So I'll give you some examples if you want to ask about that tomorrow. So I don't want to get super controversial right now. Things that people don't believe in that might actually be true. If you pick that to be true, and I ended up picking my null hypothesis, my null prior, I'll say pi theta on the null space and pi theta on the alternative space, there really aren't any choices for this right here. is just one point. So how do I smear mass across one point? I do it the same way everybody else would do it. And my smear would look like a point of mass on that one thing. So I don't have options for that. So you just place a delta function on this. When theta is equal to the null hypothesis, so I might make that theta naught right here, or I could write it something like this. Theta naught, lots of ways to write out the same thing. So it's just an indicator function. Indicator theta is equal to theta naught is just equal to a 1 or a 0. And this is if theta is equal to theta naught, and this is otherwise. So I could do the same thing over here, but I could put that point mass on the one point in the alternative space. So if I did this and I didn't multiply by any funny constants in there, and I just made sure that these look the same, so it's just a funny way of multiplying by 1, we would come up with the p-value. Again, the test statistic that I'm assuming the Neyman Pearsonian or the p-valuist is using is the one that falls out of the likelihood ratio test. So same statistic. So the p-value would be equal to the probability of theta naught given h naught, given the data. So this is just h naught. It's a really simple hypothesis. So you would have this semblance between the two different paradigms. The p-valuist and the Bayesian agree with each other. So that might seem surprising. We're supposed to always fight with each other. A lot of the things are similar. So we've seen that there's a lot of commonality in estimation between Bayesians and non-Bayesians. We kind of see that if you're using reasonable priors, the estimates might limit into each other. And having those penalty terms could be beneficial with some examples. So the binomial example when p is small or big is a good example of why you might want to penalize part of the space. So there can be some differences between a Bayesian and a non-Bayesian, but I would say there's a lot of commonality between the two groups. And these different types of tests that we just wrote down, one-sided and the sharp test, there's total agreement. And I would say it's because the hypothesis is really clear what it means. Is it theta naught or theta 1? Is it this side of the interval versus this other side? And I would say there's a full balancing act between those two spaces. This space is just the same size as that space, so that seems reasonable. And in the one-sided case, the size of those sets is the same as well. So some agreement. Let's talk about the sharp test. For the sharp test, or simple versus composite, or however you want to phrase this, or I call it maybe the point test or something like that, point versus an interval, so theta is equal to theta naught, I mean at that time, theta is theta naught, versus its complement, theta is not equal to theta naught. If I wanted to test something like this, we could already see there's an imbalance in the size of the sets that we're even making a comparison. So I would love to be able to say, I should just look at this and go, there's a huge problem with this. I didn't think that there was a huge problem when I was taking stat 101. I just did what they told me and I got my A and I soldiered on. So didn't know what the controversies are in doing this. Let me tell you a few of them real quickly. So what would happen for the p-valuist, maybe the Neyman Pearsonian, or the Fisherian, or however you want to think about all these different guys, there was commonality there between those, the Neyman Pearsonian and the Fisherian. So it's just that they decided to argue with each other. So even instead of, they're kind of talking about the same thing and trying to address each other's concerns. So the Neyman Pearsonian will come up with the z-score. I'll call it Zn. That's just xn bar minus theta naught over sigma over root n. And that's specific to the normal problem. And we've derived something like that. So this is the test statistic you would come up with, and this would induce that power curve that does this. You know, it comes down at a point and it goes up. So it's basically the combination, the union of those two different power curves in a recalibration so that it has the right alpha level. But basically, you're taught to write this down is the test statistic for testing this hypothesis. Basically, how far is x bar from theta naught? Keep in mind, x bar is converging to true theta. And so we want to see the distance between those two things. And I think this is a good idea. Obviously, this is part of the information is how far apart are those two things. So if, I'm just going to imagine, and we're going to do a thought experiment right now. This doesn't exactly happen with real data, but I still want to think about what does this number mean. So let's imagine this number was 1.96. So that would relate to a p-value of approximately 0.05. We'll call it 0.05. So this isn't exactly that number or that number. They're really close to each other. So if somebody told you the z-score was 1.96 for this hypothesis, you'd say p-value 0.05. So, and if you want to make this plus epsilon, so this is minus some other number, I'll call it epsilon star, you can do that. So that you can make a decision. This is the point Fisher's making. That if I subtracted epsilon, I would make a totally different decision. And I sympathize with Fisher. Obviously, there's an issue there. Neyman and Pearson said, we're not saying that, we're just telling you what it means mathematically. That p-ducking alpha as a calibration of the error rates. So, 1.96, we'll get rid of this. I think you get it. P-value 0.05, you make some decision. What do you do at 0.05? They never told us. So, good news is it probably doesn't happen too often. You could include it and reject, or you could not reject, it doesn't matter. Probability 0 in this example of it happening. So Zn is this number right here. Let's think about what happens when n is big. So let's think about if n is big. We'll think about different things as big. Let's imagine n was a bazillion and I got this, 1.96 plus epsilon minus epsilon. What do we do? What did Neyman and Pearson not say to do? Okay. What do we believe they said to do? Say our alpha level's 5.05. Reject. Reject. So you reject. Okay, let's say if n was 10,000. What do we do? Reject. Let's say 10 million. What do we do? Reject. Billion, what do we do? Reject. So it doesn't matter. It's just a rejection. This is where the Bayesian and the non-Bayesian totally disagree with each other. So let's just play this thought experiment. Instead of just making that number big, I want to think about what happens in the limit and just analyze this. So limit n goes to infinity, Zn, limit n goes to infinity, x bar n minus theta naught over sigma over root n. I like to put the n there because I'm going to treat it in a second. I like to remember that's a function of n. And let's just say this is 1.96. I do agree this wouldn't happen with real data. You would have some fixed hypothesis, and that wouldn't just continue to be 1.96 all the way across the space. So we're just asking this question of what happens if it was absolutely astonishingly big? So same thing would happen if you don't like my n is equal to infinity. Take 10 billion, raise it to the 10 billion, do it again, do it again, do it again, do it again, do it again. You get the idea. Will converge to the same answer. What is this converging to? 0. So what does that mean this is converging to? If this is going to be fixed. 0 as well. That has to converge to 0 as well. If you know what a derivative is, you understand that. So if you don't understand that, you never understood what a derivative close. It's the limit of these two things going to zero simultaneously. It has to do with the rates at which those go to zero. So for this to be a fixed constant, this has to be going to zero at the same rate, but just 1.96 times faster. So this is going to zero at rate 1 over root n, would be the asymptotic rate, and this would be 1.96 over root n. They still have the same asymptotic rates, this is just happening 2 times faster, approximately. Cool? So what does that mean about the hypothesis? If n was astonishingly large, I would agree. If this is 1.96, you're still 1.96 standard errors away from the null hypothesis. So, but that standard error is tiny. It's vacuously small, and if I take it to the limit, it's as small as you can get. So, this distance might be 1.96 standard errors, but if n was super huge, theta's right on top of theta naught. It's really close, and you can make that as close as you want. And so, in some sense, it's not theta naught, and you're able to distinguish it, if this is true. So this would be like somebody says, I'm going to hypothesize a coin is fair, but I find out that the true coin has probability 0.5000001 probability, and I can be absolutely sure it's not fair. And so I say, statistically significant, reject that 0.5, get rid of it. It's not true. And that is a true statement, and the question is was that meaningful? So it's kind of like a COVID thing. Vaccine works, how much did it work? So how much did it help? I think we should be asking those questions. Masks work, how much do they work? How many lives do we actually save? So it's like 3, something like that. What was the trade-off? Okay, that's a different story. So we have to ask the question, not just is it effective, but how effective is it? Is it worth the trade-off? And I think we should be thinking about this. And this is probably where a lot of the controversy arises from. A Bayesian is going to feel very differently about this answer. So Z 1.96, they're going to make different decisions depending on what n is. So let me tell you what a Bayesian will do. The Bayesian is going to use a prior of this form. I'm going to say this is my total prior, pi theta. It's just the sum of my null prior, my alternative prior. Those are the only 2 things. Bayesians are working in probability spaces, so they union, they add. So they do all the same probability rules. So they're going to do this. Pi naught, theta is equal to theta naught. This is how they smear mass on the null space. So this is like pi h naught theta plus 1 minus pi naught, my alternative weighting, times some alternative prior. This is where the controversy is. So let's say I use the normal prior. That's the conjugate prior. And I just picked it to be something like this. Where would I want to center this? Probably theta naught. So if I were testing theta naught, why would I want to center it at 10 billion or something like that? That would be really bizarre. So that's not controversial. This part is, and maybe the form of that is. So keep in mind, this is putting a lot of mass on theta naught for both the alternative space and the null space. So some people advocate different forms of this prior. Some people will change the tail behavior. I think those are all good ideas. That's where the Bayesian arguments might be. Asymptotically, you get very similar behavior regardless. I don't want to say that too strongly because there is a difference in the rates of converging to the different hypotheses as a function of n, and we just don't have time to talk about all of that. I'll say this is a reasonable first step, and at least we can do the math and analyze all of this and not come up with something computational where we have to do this long-winded MCMC and we don't know what's going on asymptotically. So this is called a point mass mixture prior. Some people will sometimes make this really diffuse. Some people will take this and make it really peaky, but not make it a point mass. Those were the early days of doing things, and people will call that spike and slab. priors. Lots of papers were written in the 90s that said if you use the point mass versus the narrow variance normal for the null, you get about the same answers. So, and it's really just a question of how you're calibrating this variance against that variance. So we can remove all those questions, put a point mass, and just think about this variance. Make your life a little bit easier. And that's what those papers said. If you do that, you'll come up with basically indistinguishable answers. A lot of people think the controversy is right here. So that's the part where most people just jump in, how'd you weight it? And then people say, oh, I did 0.5, 0.5. Oh, okay, cool. Moving on. And they missed the part that they should have been staring at, and it's this part. This is a big deal. So what we would do with this is we could follow this same schema. I could integrate over this. What would I plug in right here? I'd plug in this point mass. Theta is equal to theta naught. This has got to be the easiest integral to do because it's only positive at one point. So it's like plugging theta naught into the likelihood function. Bam. So when we do that and we do that integral, we get rid of this. Right here, we just plug in theta naught. You know what that likelihood looks like. It's the Gaussian limit. And then this one right here, you do something similar, but now I've got this normal prior. And you know how to do this integral as well. That was one of your homework questions. So it's to integrate a normal against a normal. And so this would give you the marginal distribution. It'd be centered at theta naught, and the variance is what it had. So I'd have sigma squared over n plus psi squared would be that variance. That's that problem you did where they asked you to do some integral in the last homework. So we'll play around with those a lot in Bayes class. We'll do them in high dimensional spaces. We'll figure out how to do this in regression. We'll figure out how to code this up and make it a useful MCMC thing and play around with these ideas. So we'll still give you the same warnings about everything. So the question is how you pick that right here. So here's some facts. The posterior probability of the null that you'll get, just as long as you pick a reasonable prior, you don't make that 0 and you don't make that 1, or vice versa. If you pick this to be any number, this will be true. If you pick it to be a half and a half, which is probably more reasonable than just any numbers, there's some bounds we can work out on everything, what these posterior probabilities of the null are. So the p-value for Zn is equal to 1.96. This ratio, if you do work it out and then plug everything, work out this Bayes factor, work this out, come up with the posterior probability of the null, we can actually write that down in closed form expression. I'm going to save us the space. I'll do that next semester, and we'll analyze it slowly. But you would work out this posterior measure on the null space. Keep in mind that we placed a point mass on the null space because if we made this prior absolutely continuous, if I integrated at that point, it would be 0. But because I place a point mass on there, I'm actually placing mass at that point. And so it's going to make this probability something that's not 0. So if I pick the pi naughts to be reasonable, not 0 or 1, then you're going to come up with some neat effects. This ratio, the Bayes factor and converting it into this posterior probability will include this value z. It will have that in there. You can kind of see it just in the numerator of this right here. So when I work out the numerator of everything and I work through this integral right here, this part contains z in it. It has x bar in there. And I'm going to subtract off theta naught, and it's going to be scaled by sigma over root n. So the z's right there in the numerator. If your imagination isn't working that good this morning because it's early, trust me, it's there, and work it out later. So Dylan's going to do it right now. So, but it's there. So Zn is there, so I can think about what this function looks like as a function of z being 1.96 and start understanding where the differences are between the Bayesian and the non-Bayesian. So here's a fact. As n goes to infinity, the p-value, if this is always true, again, that won't happen with any fixed data analysis. And if you don't like that, just make my n goes to infinity some huge number and see what the differences are. But the p-value is going to be 0.05 regardless, minus epsilon maybe. So we reject and we know what to do. Regardless of n, this is a constant. That's because of this. The posterior probability of the null, given our data, and I could condition just on x bar because that's the sufficient statistic. That's the only thing it depends on. Doesn't matter how I write that out. This thing is going to go to 1. It's going to climb up to 1. So for fixed z, and basically it's saying theta is really, really close to theta naught. So that's as long as this number is fixed in a constant. So that's for sigma squared equal to a constant. How fast it climbs to 1 has a lot to do with that number. It has a lot to do with n, and it has a lot to do with that alternative variance. This is kind of a good fact. I like this. I think this is the right behavior. I think this is what it should do. This is what I would want it to do. I don't care about that statistical significance stuff. I mean, if that really is the question, if you work at CERN or something like that, and you're colliding particles into things to try to detect something that's super small, I want to know if it's there or not, and the smallest signature is good enough for me. So I would agree in that case that maybe it's a standard error game, but in a lot of the problems I haven't worked on, it's more like, are you close to the null hypothesis? Is really what we want to know. So it's really in context of this. Is when is it valuable? Here's the rub, is that the posterior probability of the null, given the data, also climbs to 1 if psi squared goes to infinity. So if I use the improper prior here, constant, I'm blowing this thing out to infinity, that climbs to 1. So that's a knob. And I can turn any posterior probability into almost anything I want. There is a lower bound on this. So if I ended up picking pi naught to be a half and a half, it turns out we could work out a lower bound. We're not going to do it here. But the lowest that posterior probability can be is like 1/6, which means there's a 1 in 6 chance of that thing being true. So for a z-score of 1.96, usually I'm thinking for an example like this, that means that there's at least 1/6 chance of it being true in my Bayesian mindset. So we can work through all that stuff. And it could be really big, but it depends on how you're comparing to the alternative. So I don't think this is a bad property. It just tells us we need to think about how far probabilistically, in some sense, do we need to be from the null before we're willing to reject it. And that's what psi squared is saying. Just keep in mind, if I take psi squared and I make it really, really big, I'm taking that whole density on the alternative and I'm making it lower and lower and lower. So I'm squashing down all the weight I'm placing on points in the alternative space by taking that diffusion and pushing it out. It always integrates to 1 under that curve. I will point out, if you use the improper prior here, you get a meaningless result. It doesn't mean anything. So it can be any number depending on how you compute it. If you compute it the way I told you, it's going to climb off to 1. And so that's a problem. So it's like we placed mass on pi naught, and now we're taking all the alternative points and pushing their mass way down. And so I think understanding that is the key to having this debate. And if you don't understand that, then you don't really understand what they're fighting over. And it's kind of this notion of relative distance. So it's not just relative to the standard error, but it's also relative to what you want to compare it to, the alternative, and it has to do with the sample size. That's what Wald told us. So Wald said, you've got to pick a theta 1, a distance from theta naught, that has something to do with psi squared, and you need to think about the whole power curve. It has something to do with n. So Wald is telling us we have to consider all that stuff, and the Bayesian is giving you a framework to boil that all down into one number. There is some commonality there. If you're just thresholding p is less than alpha and doing that, there's no commonality. So in this particular test, people just don't agree at all. Let's just see what people have said about this. I just want to take 5 more minutes and go over these handouts that I put up on the website, and we'll conclude with them. What I would say is the take-home message in this class: use likelihoods, do estimations if you can, set up reasonable hypotheses if you want to compare a point to an interval or something like that. Make sure you're thinking very carefully about what extreme might mean and how far from the null you would need to be before you're willing to reject it. Make sure that has scientific grounding. So if you can't think about that and you're just looking for a robot to tell you the truth or tell you something it will, it just might not be meaningful. Okay, a couple little handouts on the web. They can be found here: BASP statement on p-values and the ASA statement on p-values. So the BASP statement, it was new a minute ago. When did this come out? This is 2015, so not terribly long ago. So let's just read through this. The Basic and Applied Psychology BASP 2014 editorial emphasized that the null hypothesis significance testing procedure, that's Damon Pearson. So threshold in p-values or likelihood ratio testing. So that's what they're talking about, is invalid. There are cases where it's valid, right? So we kind of saw that, but maybe for the point test or what they see in psychology a lot, maybe it's not. And thus, authors would not be required to perform it. So he cites Trafmael. Do you know who that is? He's the editor. He's citing himself. So it's a self-cite. However, to allow authors a grace period, the editorial stopped short of actually banning Damon Pearson. The purpose of the present editorial is to announce the grace period is over. From now on, BASP is banning Damon Pearson. Threshold. So, yikes. Question 1, will manuscripts with p-values be just rejected automatically? No. If manuscripts pass the preliminary inspection, they'll be sent out for review, but prior to publication, authors will have to remove all vestiges: p-values, f-values, statements of significance, blah, blah, blah. Right? What about other types of inferential statistics, such as confidence intervals or Bayesian stats? Confidence intervals suffer from an inference problem that's not very different from that suffered by Damon Pearson. There's a one-to-one in most problems. So it's going to give you a range of values that you would have rejected. That's the whole pivoting game. So it's like x bar plus or minus 1.96 times sigma over root n. So that will be the CI. So they say, no, you can't do confidence intervals either. Those are banned. And this is where I think things get a little bit, I don't know if I want to be on the side anymore. So I kind of like that. I think it's funny. My younger self would have reveled in this. I don't think we should ban things. I think we should be considered and talk about when they're useful and what kind of tests we're doing. So do the full power analysis. I would have rather have seen that. Bayesian tested procedures are more interesting. That's a subjective comment. So you're interested in what you're interested in. So that doesn't mean anything. So he's putting a lot of weight on what he finds interesting. The usual problem with Bayesian procedures is they depend on some sort of Laplacian assumption. It's really tricky language. Bayesians don't speak in that language. So we can already tell he's not a card carrier. So like you guys will be eventually. So he's coming from his vantage point, but he's basically saying you need to use some sort of maybe diffuse prior, and it's not quite clear how you pick that prior, the problem that I was alluding to. How do you pick chi-squared? So anyway, they banned everything. You can read through that, and they say that basically you have to get rid of all this. And the problem that they're incurring is that people are doing surveys. They're sending out zillions of surveys. They're getting back fractions of zillions, but it's still huge back, so you have selection bias. That's a different problem that we're not addressing. And it's huge, so you're always rejecting. There's a small difference between the truth and the null, but n is huge, so you reject everything. And they're getting sick of it. It's like automatic pilot. I've got a hypothesis, reject, pay me my money. So I could have done that for free. There's another I'll call it an op-ed. ASA statement on p-values and purpose. They go through this. I think that there's some good comments. Why do so many colleges and grad schools teach p is equal to 0.5? I think it should say alpha, but that's a nuanced difference. This guy, Kopp, knows what he's talking about. So maybe he said it right. Because that's what the scientific community and journal editors use. Why do so many people still use p is equal to 0.05? Because that's what they were taught in college. So there's this circular thing going on. It's just going to go on forever. So they have some really good quotes in here, and you can read through it. So down here it says, this guy Jeff Leake responds, the problem is that people use p-values poorly. It is the vast majority of data analysis is not performed by people properly trained. And I don't like that argument either. It's saying that only I can do your data analysis and you're not allowed to. And that's nonsense too. So why is it so complicated? Even my card-carrying friends seem to get confused over this stuff. Lots of debates. Regina used to work here for Virginia Tech. I don't know if you know that. She wrote a good paper on this, and she has some opinions as well. Some of them I agree with. Anyway, they go through this and they talk about what they're supposed to do. And so they commissioned a bunch of different groups. Here are just some quotes. They got those 2 different commissions. And unfortunately, I don't agree with what any one of them said you should do. They just kind of balked. And they didn't give strong groundings. The Bayesians said reduce the significance level. Don't use 0.05. Basically, because of this 1 in 6 bounding, it's just not strong evidence against the null. Why don't we use 0.05, 0.005, or 0.001? And I'm like, oh man, the same exact game is going to be played. David?
It seems like if you're going to ban something, you've got to not waffle on what you're replacing with.
Yeah, unfortunately, these are people. So, and the editor's going to change and all of that. So I don't know what the right policy is on this. Anyway, what I want you to take home is that there is commonality, but the SHARP test needs a modification of the question being asked probably. There are cases where I think what David and Pearson are prescribing is useful. There's cases where what I think the Bayesian is describing is useful, but you still need to think about it. If you're just doing that on autopilot, you're bound to be caught up in the reproducibility crisis and just saying stuff that's nonsense. If you want to just reject every hypothesis under the Bayesian setup, use a continuous prior on the null, and you'll just get 0 every single time, and we don't even need to mince over it, and we can stop pretending we're not doing science and just show people it's not scientific. Anyway, you need to talk about your distance from the null hypothesis. And if you're not willing to do that, try to figure out a way to answer your questions through estimation. That's all I have for you. I'll see you tomorrow night, and we'll do yes, no, maybes and gear us up for the final exam. None of that conversation will be there. Thanks, you guys. It's been a great semester. I've really enjoyed it. So thanks for bringing the energy. I know it's hard at 9 o'clock in the morning.